Hello, everyone, and welcome to our webinar today, Achieving AI and Machine Learning Operational Excellence, and thank you for attending. My name is Blair Fleming, Open Data Group's Director of Digital Marketing, and I will be doing the emceeing today, and we'll introduce our speakers in a moment. But before we get started, I wanted to cover a few housekeeping items for you to be aware of. At the bottom of your audience console, there are multiple widgets you can use for today's presentation. If you have any questions during the webcast, you can click on the Q&A widget at the bottom and submit your questions. And also, with so many people listening on the call, we will do our best to answer the questions at the end of the webinar, but if we do run out of time, we will answer all questions via email after. If you have any technical difficulties, please notify us via the Q&A section, and we'll try to troubleshoot the problem for you. And finally, be aware that an on-demand version of the webcast, as well as the slides that are presented today, will be available approximately one day after the webinar, and we will be sending those to you via email and also available through our resources section on our website. Next slide, please. Thank you. Quick overview of who we are. At Open Data Group, we help companies achieve machine learning and AI model operation to operationalize and deployment through our products and services. Along with our software technology fast core, our world-class data science and model lifecycle services team has a highly differentiated skill set and a proven track record of accelerating and ensuring the success of machine learning and the AI journey within large enterprises. We are pleased today to have with us both Garrett Long and Regan Avon. Garrett is the Vice President of Marketing at Open Data Group and holds a BS in Electrical Engineering from Carnegie Mellon University. And at Open Data Group, Garrett focuses on helping customers understand, develop, and implement strategies for effective model operationalization. Sorry, Garrett. Regan is our product manager here at Open Data Group, and she has a background in integrated systems engineering. Regan previously held positions in stimulation engineering and operations at United Airlines and Honda, and she has taught introduction courses in data science and web development at different MBA programs across the United States. She's also the founder and coordinator of the first Women in Analytics Conference in Ohio, and remains active and involved in fostering collaboration around emerging analytical methods and technologies. As for our agenda today, we have just an introductions, but we are going to be going through market trends and why we are talking about the importance of machine learning and AI operations. Then we'll be defining core concepts and implementing model development lifecycle within our organization. And then we'll go through a few examples of abstractions, as well as wrap it up with a quick Q&A at the back end. And with that, I'll hand it over to Garrett.
All right, thanks a lot, Blair. Just appreciate everybody joining today. I saw the list of attendees and appreciate some folks joining for several of our webinars. Glad to have you back, and for everybody that's new, also glad to have you here. And I just want to spend a few minutes before I turn it over to Regan to give some context of why we're talking about the deployment and operationalization of models, machine learning and AI being a very hot topic in the space. And I think this Gartner chart really says it all, is that we see the business impacts of these machine learning efforts and projects across a variety of industries and companies. The value is not really being realized because models are not getting fully deployed into the line of business. And so here at Open Data Group and with our customers, we help to focus on that next step in the chain after creation is how do we ensure we deploy the models to gain that value to the line of business. So our mission is all about the journey towards using the models being created by these talented data science teams in the Fortune 500 today. And really, it's all about the transformation projects that are happening. And really, we see transformation in our customers is driven by improving decisions, not in particular by improving anything about the compute infrastructure, data, or models, but it's a combination of this stack that allows the companies to drive decisions, which drives value. And what we're finding across this stack as we move up from compute to data to building models and then making decisions is that there's a technology component and an organizational component. And these two components must align to create value. And today we're going to spend most of our time on really the model development lifecycle, what we call the MDLC, and how that helps an organization get ready to implement and then consume these machine learning models. So we look at it as a amplification of each other. Generally, we're seeing in the market today this kind of stack where we're starting with business issues to solve for. We might find some data in our lab. We're going to pick some algorithms. We may even do some assessment on that model. But then as we start to move that model into production and connect to production data and deploy it and then monitor, retrain, and manage its lifecycle, that's really where a lot of organizations are challenged today. So what we're after on the full stack is to develop an appropriate capability to drive routine value out of these models. And we're also providing technology that we hope solves for some of the operationalization challenges in the market today. And Reagan will take us through the details of the MDLC in just a moment. But just to say it for the folks on the phone, the technology we provide is called FastScore. We're not going to really talk about it much today, but it is a universal deployment solution that integrates to several important factors in the infrastructure, including all the machine learning and model producing workbenches and libraries. It connects to all data sources and then is deployed actually as a Docker container, so it can connect to all the compute and orchestration layers out there. And FastScore is really about kind of making this universal, independent of creation capability. And that it allows us to do some interesting and valuable things, including model workflows and scheduling models for build and train and redeployments, and also some really interesting aspects around model tracking and assessment. So our technology is FastScore. Again, we're not going to talk about it except for this slide today. Just want you to know that we do see it as a two-pronged approach, technology in combination with service. And the model development lifecycle, which is where we are going to focus nearly all our time today, is all about helping teams accelerate the collaboration, remembering that this is a multi-team situation. Certainly there's data science and data engineering, but also IT and product management as well. And also trying to set up the accountability and traceability across the organization to ensure the value is being created out of these machine learning models. So with that, just a quick summary that we are helping companies today, our customers, put models into production. It's what we do. We have, an opportunity, we think, to also provide some process and viewpoints we're going to go through today, really customer tested methods to help scale out these production requirements. And then together, these things drive the transformation in the enterprise. So with that, I'm going to turn it over to Reagan, and she's going to take us through some of the details.
Thanks, Garrett. Yeah, I want to just start with what this model development lifecycle looks like. So I think we're all pretty familiar when you think about building machine learning models that there's a model design component. So this is the time where the data scientist is sitting down with the business and trying to understand what problems they're going to solve and if machine learning is a good solution for them. They're trying to gather data, understand relationships amongst the data, and they're doing a lot of experimentation. So once they've got all of these different experiments, they've got a deeper understanding of the problem they're trying to solve, a deeper understanding of some of the potential solutions. They may have a few candidate models that they want to actually pit up against each other and understand with production data and pros and cons of scalability and accuracy of that model, what's going to perform the best for that use case. And can we get those outputs put into the right operations or production systems that will enable the business to derive the value from all of those efforts. So this model development lifecycle will enable those companies to do that very quickly and rapidly and with high quality. So a thorough understanding at each phase along the way. And what I'm going to focus on today primarily is this post-experimentation, post-model creation and development component, although it is very, very related. So all of the models that are being built in these workbenches that data scientists are using have to get out of those workbenches. It might be a data scientist who has a dedicated cluster of Jupyter Hub that they can access, and they can go in and build models and scale those models while they're training them on test data. Or it might just be some local, more simple statistical model that they've built in our studio on their own laptop. So in either case, there's this idea of moving models around and it consuming different sources of data. So I'll walk through some of those challenges experienced on its journey to production. So some of the challenges I'll talk about today, and then the latter half of the webinar, I'll get into the solutions that we have been using and the core abstractions of the solution. So it's the number of changes that the model actually experiences along its way to production, the diversity of the teams involved, and the rapid iteration that happens once models are in production. And it might be different for different types of models and use cases, but we've seen the need to be pretty consistent across what we've experienced in our customers. So those volumes of changes I'll walk through in detail, but I think it's, I come from a systems background, and being able to be agile with models and machine learning models over time and have a quick process enabled by organizational processes and also technical support and technology to support those processes is important. So the first we'll focus on is the volume of changes that the model experiences. So the data locations, the data that it's consuming are going to be in different locations as it moves over time. You can think of during testing, the data scientist may have exported some data fields from different databases and aggregated those together and started to create a file, maybe locally, of attributes that they want to use in experimentation and a certain number of rows so that they don't run into scalability issues. And then they've got this, CSV file that they're working with in their lab environment, but it may not run off of that in production. So it's going to experience changes over time. Similarly with infrastructure, we have to think of security, access controls, who can access that data, who can access the code, the model code. And all of the surrounding systems that we so commonly see for software in the software development lifecycle. I think those are very, very applicable and necessary in the model development lifecycle as well. And we just haven't really forged that journey yet in a lot of the enterprise that we've seen. So for the model itself, as I mentioned, it may be consuming some data from a dev database where the PII is removed, or it's more of a playground that data scientists have access to in a dev environment. Similarly, as it moves towards production, it may move over to a UAT or pre-prod database with certain permissions on that. And when we finally get to production, the model is going to consume production data with no access, assumingly, to the data scientists. And the outputs are going to be actually consumed by the business unit. So whether that's an application, a dashboard, or it's just an output of a report for some business user, or it's going to be fed into your product that is exposed to actual consumers. So it's both the input and the output data are going to experience different sources across the different environments. And similarly with the model environment, as I mentioned before, maybe there's some dev cluster for the data scientist to build. And as it starts to progress, it may need access to more computational resources to understand the scalability of that particular model. So the end user is going to have some latency requirements for that model. Maybe it's a real-time model where certain activity on a website is going to drive them to a new experience. Or maybe this model just needs to be ran in batch mode and it's okay for it to run for 3 days. But regardless, the scalability components and characteristics of the model have to be understood before it gets deployed to production. And the only way to do that is to understand the outputs of, memory and CPU utilization, records per second, understanding its current capabilities and what happens when you change certain dials and tune the resources available to that model over time. And you'll want to make sure that your production environment is capable of providing those requirements for latency. So how do you move things to different environments with statistically sensitive code, and hoping that, you know, the environment will contain all of the necessary libraries and the model language itself. So, you know, each of those environments has to support that model language, or you're going to run into something like recoding the model into another language that someone believes to maybe be more scalable, or is only supported in the production environment that you're deploying to. Similarly, a lot of these models, if they are open source, require a series of libraries and very particular versions of those libraries that it must run with. So every single environment as you move has to support the exact same type of libraries and versions. So some other components that will change for deployment, you know, as you move from dev to production, obviously your source code management system is going to be more open, so you can make changes during dev. It's going to be more restrictive as you go towards production, and you're going to want it to be read-only as the model's actually running in production, so nothing can change any of the code and you don't open yourself up to vulnerabilities. And metadata will need to be captured along the way as well, so that you have pure auditability of that model and you can reproduce exactly what happened in each environment with different data sets, different versions of your model, maybe different coefficients that you've created during the training process. And again, security, as you might imagine, will get more and more restrictive as you move towards production. So how do you ensure in each one of these environments that every single piece of this entire machine is properly locked down? The second challenge I'll walk through are the diversity of teams involved in this process. So what we've identified, there are 4 core teams that are truly involved, and one would be the business. So the business or the end user of the model that's really driving the reason the model was created. They understand what the customer is going to need. They'll probably have some product managers on their team that are defining requirements for this model. If you're making, you know, a website where you're trying to change the experience, what does that look like? What does that mean? What kind of latency requirements are you looking at to ensure that that experience matches the expectations of your users? And similarly, if it's a business unit, you'll want to ensure that that business unit is truly understanding and deriving value from the outputs of that model, and that it's making a significant impact on their decisions. And then there's IT, who is very concerned about security, infrastructure costs, and high availability, and disaster recovery. So all of these other components from the computational side, they want visibility to that, and they want to understand and control their components of this entire process. So running the model in, on-prem or in the cloud, and what does that look like, and how can we expose those decisions that they have to make and that they're ultimately responsible for to be able to move this process faster. The data science team, obviously, their job is to build an impactful model that's going to derive value for the business. So how can they ensure that and feel comfortable and confident that that model's going to do what the business wants and what they need? And how can they also be enabled as a team and a user of technology and services that are provided by their IT teams in a very efficient way, so that we're not caught between those two teams? And then there's engineering, whose job is to automate and scale and improve the implementation of these workflows. So, they're going to want to look at stuff like schedulers, and they're going to want to look at things like automated testing and the scalability of these models in production. So ultimately, this is code, and they, have a lot of experience in the SDLC, or the software development lifecycle, that actually translate over to the MDLC, or the model development lifecycle. So these 4 teams need to talk to each other and work with each other very efficiently. And as you might imagine, there's a lot of handoffs that happen between these teams at various moments throughout the entire process. And if you can set up expectations and set up the proper abstractions between them, the efficiencies of back and forth, and quick feedback and quick movement that is prepared and high quality to the next team or person making a decision on the deployment happens much faster, and you're not stuck in these 6 to 8 month long projects of getting a model deployed. The third process challenge that I'll talk about is this rapid iteration. So I always think about the rapid iteration as a 0 to 1 and a 1 to 100. There's the first time you deploy a model into the wild, and then there's the multiple iterations that happen after that. So the same thing with product management, getting, you know, your first iteration out there. There's going to be things that you want to improve upon and things that will actually change while it's in production. So you'll gain a lot of insights about the model, and you'll want to make sure that that deployment process is quick so that you can make proper updates and proper adjustments to your deployment and your model, and the supporting infrastructure and technology for that model to ensure that it's going to run to the best of its ability. So here are some of the things that change after deployment. What if it stops running? You know, what could be the problem? What are some of the root causes of why it stopped running? And you'll want to obviously fix that if it's a mission critical or business critical model that's running in production, maybe feeding a live site that you have going. If your company if the bottom line depends on this model, you obviously want it to be high availability and to run. So how can we expose the individual diagnostics about the model to be able to understand why it would stop running? So it could be a data structure problem. Maybe the model didn't expect a particular type of data that it received. It could be an environment update where the model is running, or maybe a newer version of the model has a different type of library that it requires. So how do we ensure that the environment's going to support that quickly? It might not run good enough. So you might get it out into production and the production data starts to drift. You know, if you've got a bunch of traffic that's abnormal to your typical traffic, or the statistical properties of the data you trained on don't match the data that it's consuming in production, that model is no longer sufficient to be able to predict on that newer data. So that's when the model drifts and the accuracy score goes down. So what do you do in that case? When do you pull the plug? When do you start automatically retraining the model on a new set of data? How do you get all of that updated in time? And the model standards might change as well. As I mentioned, the 0 to 1, getting it out there, but then the 1 to 100 are all of the improvements you can make on that model. So as the standards start to change, we may require or demand or expect more from that model over time. And how do we get those changes into production? Similarly, if the model doesn't run fast enough, is there a different type of data transport that we can link up to the model? Maybe we're using one particular transport with certain settings on that transport, and we can adjust and tune that so that we have a better way of delivering data to downstream applications. And we can also scale that model. So what does that look like? Do we just throw more resources at the model? Can it run concurrently? Can we increase the number of instances of the model running? And then who's ultimately responsible for all of these changes? And again, how are you aware of the changes that need to happen? How do you communicate it to the proper teams? And then how do you get that change into production quickly? These are all problems that we focus on from a process and technology perspective. So I just walked through these top process challenges that we've observed over time. Now I want to give you some solutions and abstractions, some ways to think about these handoffs and some of these problems that we've been solving. So creating meaningful abstractions or handoffs to supplement the process is going to be very important. So we've identified some very critical abstractions, one of them being the model coefficients. So if you've trained a model, it may have some weights that it references while it predicts. So out of your training session, you'll have, a training set of data. You'll have your training model code that will take that data, and it will produce weights, coefficients, statistical properties according to whatever type of model you use during training. And those may be updated daily, maybe updated weekly, but this is what, if those statistical properties of the data are what you're using to predict in production, you'll want to make sure that those are accurate over time. So you'll have to really understand the SLAs on performance of that model, the accuracy of that model. And of course, an execution ready model, there's a lot of code involved in the experimentation process. If you're not familiar with what that looks like, you should sit down with a data scientist and look at their Jupyter notebooks on all the different methods that they tried and all the visualizations they looked at and trying to understand all the relationships. And not all of that goes into production. Only the code required to score will go into production, or only the code required to train, if you're running that on production systems, will go into production. So having an execution ready model or a scoring model is important to keep that separate from the rest of the code that happened during training and experimentation. The third one is the model data definitions. So for every model, it expects a particular set of attributes or data that it will consume. And those attributes have a very particular type that they assume that they're going to receive. And if in production it receives data outside of those expectations, the model could crash and stop working. So we want to set those expectations and assumptions on the data being received and produced, so that people have something to look at and say, this is the definition of what the model produces. If I'm the downstream application engineer or developer, I can say, when I make a RESTful call to this model, I can assume to get this data back and this type. So I can start to say either, yes, that fits our requirements, or no, it's missing something, please make adjustments. Similarly, the data transports, how is the data getting there? As we mentioned, it changes over time. So whereas in the lab environment, it might have been a CSV file, in production, it might be from S3 or HDFS. So we'll want to define those particular types of ways that the model is going to consume data and be able to change them out very quickly. The next one would be around model environment requirements. And I mentioned this a little bit earlier, where we've got a set of required libraries and versions. These are code dependencies. Maybe it's a custom library that the data scientist has built that maybe does some feature transformation. And we'll want to make sure that all of that is available and acceptable as well in every single one of those environments. So as we can start to talk to security, they have something very tangible and specific to look at on what's being deployed and what's necessary. And if there are issues, vulnerability issues, those can be addressed earlier and not when we're actually trying to push to production. Performance monitoring models, these are statistical reports about the model. So how do we know if the model is running properly within some sort of range of acceptance? So that's really the data scientist working with the business teams and saying, what's acceptable? How many times is the model allowed to be wrong, and by how much? So that we can understand what the threshold of accuracy looks like in production. And if it goes outside of that range, we know we need to do something. So we have a series of monitoring models that are understanding performance, that are very specific to how the model is created and how the model is being used. So we'll want to understand how that model is being used at all times, not just while we're testing and developing. And then lastly, the sensors, which expose the computational performance of the model at all times. So is it not performing because of the model itself, or is the bottleneck actually in the input data? Do we need to change something about the way the model's consuming data? and really truly quantitatively tuning the performance of that model while in production.
Right, and I think I'll jump in there, Reagan, real quick and just say that, we're not going to cover the technology, but as we go through, these ideas of the connections and the abstractions, an important question to ask yourself and your teams is, do I have a truly an independent capability to deploy and manage any model with these types of abstractions in mind, right? So it's really about that kind of uniform and uniform approach supported by technology that we found really helps to scale this effort.
Yeah, I think that's a really important point, Garrett. The standard is what makes these practices really effective, because the expectations, when new teams are onboarded to create models and get those into production, the expectations and best practices are there, and they're supported by the organization fundamentally and also technically.
Right.
So we'll start off, we'll actually get into some of the examples of what I'm talking about for these particular abstractions, and I'll show you actually a little bit of code. So the model execution code, as we mentioned, that scoring code that's actually going to do the predictions in production, kind of would look like this as an example. So if you had a gradient boosting machine, at the top, that's some fast score language there, but the rest of that might would probably look very familiar to a data scientist or a statistician. So importing the required libraries that it needs, and then really doing the transformation on the data that's coming in. And at the bottom, you'll see this .predict function, which is just taking in data into a data frame, and it's going to do the GBM fit.predict, and it's going to output this score or this prediction. And really that's what this is. It's a function. So it consumes data from somewhere, and it will make its prediction or do its calculation or statistics or math, really, and then it will output a score or some other data that will be used by the downstream applications or the business unit. So this is what the execution code would look like. And notice it doesn't include any of the other components we talked about. It's abstracted away from everything else. So it stands alone. And this particular piece of code may not change. So when we retrain, we might see that, okay, the retraining produced different coefficients, and those different coefficients will change, but the model itself that actually does the math and executes against those coefficients does not change. So we don't have all of these code changes happening every single deployment. So if you can see here, there's a GBM fit .pickle file. This pickle file contains those coefficients or the model weights that I referred to earlier. So you can imagine that this model would take in different coefficients or different updated weights after a retraining happens. But this model's been blessed and it already sits in production. It just waits for those updated coefficients, and then it will execute against that. So the model itself is really a combination of how it's executing against the data and what coefficients it's referring to. So you can think, if we were thinking about model lineage, we could say this run was running with this data from this source with this execution code in this environment, referencing this particular set of coefficients created by this particular training data set. And we can now get a thumbprint or a unique identifier of that model and truly have the ability to audit. The second would be the schemas I referenced earlier. So what does this model expect to calculate against? Here are two examples of what that particular model would expect. So the data scientist would be responsible for creating that execution code and also creating the schemas. So that on the left, you'll see the input schema that the model requires, all of the attributes and their types. And on the right, you'll see the schema for the output. So it takes in a bunch of information about a car, and it will output a prediction that's some number that represents the riskiness of that car. And these live with the model. Unless the model fundamentally changes and needs different data. In that case, what needs to change are the schemas and the expectations of the model, but also how the data is being delivered to that model. Which brings me to the next piece, which is the data transport mode. So how is that data being delivered? So in this, just to go back for a second, in the schemas, it doesn't matter how the data is being delivered in this particular case. You're just stating a contract of what data exactly and how the data type should look like when it is delivered. And this really gives a baseline for a data engineer to come in and say, okay, I have the requirements of what you need, and now I'm going to go to the source of that data and find the best way to get it to your model. And so an example of that would look something like this, where on the left we have an input type of transport. So it would grab data from a file called inputdata.json, and then it would output the outputs onto a Kafka topic. So as you can imagine, moving a model from training all the way through to production, all we have to do is update these files that say, here is how the data is going to be delivered to the model. So as we move to production, we can just say, okay, part of the promotion criteria is that we have the exact details of this very particular Kafka topic we're going to use in UAT or in prod. And those are managed across that promotion cycle. And then you can also imagine not only are the sources changing, but potentially you can move an application from being batch to on-demand or streaming. So if we want to just change this from consuming something from a model or a bulk query that's pulled once and that it references and scores against to a Kafka topic that will read at real time, we can do that very, very easily. And then that entire component could potentially have multiple languages. So if you think about the execution code, maybe it's not just Python, maybe it's R, maybe it's Java, maybe it's Scala. And if that's the case, then we need the environment to be language agnostic. And one way that we've looked at doing that for that particular abstraction, to abstract it away from the infrastructure, is to go the microservices route, where it actually has its own image and container and can run in that container with these other abstractions that sit in infrastructure that can be moved around. So if I have it deployed in a container on premise and I want to move it to the cloud, it's abstracted away from that particular infrastructure, and we can do that very easily. So as I mentioned, all of those challenges in the beginning, these are the particular abstractions we've chosen to use to make that process happen much quicker. And then those microservices can support things like different versions of Python and different versions of libraries, and those can be managed much more easily than trying to ensure that the server it's running on supports that itself. And then this is what we consider to be a unit of execution for a model. That container with the execution code, clear definitions on data coming in and leaving that execution code, and ways to transport the data to that particular container from its source. And we can do a lot of scalability activities around this as well. So the other component was model acceptance, and we can actually set up multiple transports outside of the container to send the outputs to multiple places. So one of the outputs could actually go to a downstream application, and a couple of the other ones can feed these model acceptance pieces of code or statistical properties so that we can check if the model is drifting over time, and we can check that if there's an alert that went off, what happened and what did the data look like at that particular time. Similarly, we can put sensors in the code and in the container itself to understand records per second, CPU utilization, memory usage, and we can use that information to tune the model appropriately as well. So just to reiterate some of these abstractions we discussed, we talked about the model artifacts, or those coefficients that the model references that can be updated up outside of the frequency of everything else being updated. We can also, we also looked at the execution ready model, what that looks like and how simple that code looked for this particular example. Then we talked about model data definitions and the schemas that we referenced earlier, those contracts of data, how data is being delivered, what requirements the model has in its environment that it's running, and how do we tell if the model is running well or well enough. And now it's time to talk about who owns what. So now that we've referenced the first set of challenges we discussed earlier, those the volume of changes that happen to that model over time, we're going to talk about who owns what and why these abstractions are important in getting organizations to work cohesively and efficiently together. So as I mentioned, the data scientist would ultimately be responsible for that execution code and the data that it expects. You could have a data engineer specifically focused on tuning and optimizing the way that the code or the data gets delivered to that code. So they would ultimately be responsible for setting up all of the technology surrounding data transportation. Model latency can be exposed to the infrastructure team, and the infrastructure team can look at the sensor outputs from multiple models across multiple teams and understand their costs and where they could scale certain models up and certain models down depending on demand and also depending on the value that that model is bringing to the business. So if you can imagine some kind of analytic operations center that the infrastructure teams can look at and reference and understand the model costs from an infrastructure perspective across multiple teams. Similarly, the business can always keep its eye on how the model is performing. And if something moves out of range or if something changes, that data would help the business team to understand what changed and to be able to work with the data scientist to make improvements that would help that model performance and ultimately the value that model is providing for the business.
Right, and Reagan, if I can just jump in on this one, I think from our customers, especially a very concrete and relatable one is the data science to data engineer relationship, right? And I just want to highlight that as a place where we see time and time again the abstraction of the data schema and the transfer of that data from the model execution code means we can have confidence that that model's never changing, right? The intent of the model doesn't change because we don't have to touch it. And I think that relationship between data science and data engineering is one of the ones we see over and over as they build out the MDLC. It's super valuable.
Yeah, I agree with that. I think the exposure to everything and not having to touch an entire system every single time. I mean, a lot of times we see custom deployments for every model, and that might be fine if you have 2 or 3 models that you're looking at. But as your team starts to identify more and more use cases for additional models to bring value to their businesses, that's not going to be sustainable. You'll actually have to hire more and more people to maintain those custom deployments. So I think this is where we see another benefit for companies to really truly have a standard way of deploying that is agnostic to all of these different types of use cases they may encounter, whether it be on demand, batch. For one particular type of modeling, it might require a neural net, but for another, it might just be a linear regression. And how do those things change as far as scalability and complexity and code management? So you'll see all of these use cases demand very unique combinations of all of those changes. And how do you create the right abstractions to support all of those? So as we mentioned, just to recap, the model development lifecycle, moving from model design all the way through model telemetry, or really monitoring those models and making adjustments and going back into redesign to create another iteration of that model, or some additional models to help the performance of that model in production. And how do we make that happen very quickly, very smoothly, seamlessly across those different teams and across all of these barriers that companies have already in place, especially in larger enterprise, to move that model through those systems very carefully and strategically, but quickly as well, and with high confidence that it's going to serve all of the needs along the way. So I'll quickly run into some of the model prep questions or details. So as I mentioned earlier, will that model have a consistent environment? Will it receive and produce the same data? Does the modeler have the appropriate tools to do model testing? So in unit testing, how can we replicate the exact environment the model is going to run in production for the data scientist? Because the data scientist might run a series of tests in creation and say, yes, it runs on my machine. And I'm sure most of you have heard that before. And then it moves out of their machine and it no longer runs for one reason or another. So how can we replicate that environment to ensure that the number of changes it experiences will enable you to investigate less on why it may not run? Of course, there's end-to-end testing. It's not just a model anymore. It's an analytic workflow that has multiple stages. So if there's an upstream data pipeline and the downstream kind of analyzers of the outputs of the model, this becomes a larger workflow. And multiple data transformations that may happen in between certain phases of a model. We can now link those together much easier, and we can keep them separate pieces of code that would be updated individually. Of course, we talked about acceptance testing. Can we get a business unit to sit down with the data scientist and look at the same outputs and talk about it and talk about adjustments before it actually goes into production? And can we actually do champion challenger A/B testing against two, the model in production and some candidate models that we've been experimenting with to maybe replace that model without a glitch in the model actually producing outputs in production? I think the champion challenger component is extremely interesting when you get to a point where one model is built with one particular method and another model is built with another particular method. And over time, can we watch the two models consume production data and produce outputs and see what the differences would be over time? So I think that's another important quality, is we can get more models blessed to receive production data and truly be apples to apples comparison on the outputs. For model deployment, I think there's a key distinction off of that note that pre-prod to a technical team may be different, or production to a technical team may be defined differently than production to a business team. So where a technical team would see production, that means that it's receiving production data, it's running on production infrastructure, it has production qualities about its security standards. But the business only thinks that's production when it's actually using the outputs in operation. So when, as you could just imagine in that scenario I just mentioned, you've got these two models that are seemingly production together from a technical perspective. But from a business perspective, only one of those models is driving business value, because the outputs are doing something. It's making a decision, it's exposing maybe new features to your users, and it's actually making something happen. Whereas the other one might just be outputting its data to a dashboard where you can see what it might be doing if it were actually running in true production from the business perspective. So I think it's important to note those two things as well. And some questions that may arise during the model performance monitoring might be something like, what is the calculated limit that would describe an unacceptable output? What does unacceptable mean? So how do you define unacceptable? What's a threshold that makes sense for the business? And what actions are taken when that limit is actually hit? So who's responsible for that? How do we set up automated alerting for the teams to respond to that immediately and everyone know what to do to make an adjustment happen? I think a big piece of it is, how do we understand the goodness of a model? How do we calculate, if it's wrong, how much money does that cost us? Or if it's right, how much value does that provide us? And can we come up with a number that would make sense for that model to be profitable? Or if it's something where the model being wrong is completely unacceptable, like in the medical field, are we able to set proper thresholds and limits that we can work with on using these types of models in more important decision making in these different industries?
Yeah, and I think if I can just jump in, to the audience, I do want to just stress that, A/B testing and model performances are concepts I think well understood in teams, in teams across the organization. But what this really is how do we make a unified approach that's scalable for the enterprise, right? So in a banking customer, that the risk team and the fraud team and the consumer-facing marketing team can all access similar techniques and similar process, so that we don't have to do this again and again in a new way, right? So this is all about kind of assembling this abstracted infrastructure and capabilities for the wider organization.
Yeah, absolutely. I do want to close on just giving an overview of this process from moving from lab to production. And I think that this will help kind of solidify these points. So as I mentioned, during the training model will output these model artifacts, and the scoring model and the schemas and those monitoring models will be committed to a dev repository, a code repository, whether you're using Bitbucket or GitHub or however you're storing your model code. So this is what the data scientist world looks like. Creating these training models that produces coefficients, potentially, it may not, the type of model may not, or, and also creating these scoring models that are production ready and the schemas that will be committed to some sort of code repository. And they can feel confident that it's going to run in production after testing. In the development environment for the code and the model, it may look something similar to this. So that dev code repository will be accessible from the dev environment. It will be, the model artifacts will also be accessible from the dev environment. And we've now added the transport types to connect to a dev database specifically, so that we can consume data from a dev database and maybe write data to a dev database and ensure that that entire process and workflow is executing properly. And this might be running in AWS and not on the data scientist's laptop. Then in UAT, it may look like this, where we have those monitoring outputs being written to some dashboard, could be Grafana or Tableau, whatever dashboard you're using, and really just getting those outputs in front of the business in a meaningful way, so that we can decide that it's passing user acceptance testing as the model performance. Similarly, we may put this in a scalable infrastructure, so this AWS UAT environment that has more availability for resources, and we can truly understand what the latency is going to look like once it moves into production. And we may still use the dev database, or we may change to a UAT database that has maybe a couple month old production data, so we can get a better understanding of what this will look like, and we can check all the boxes. And in production, we may commit all of that code to a prod repo that is read-only, and take all of that code and put it in the exact same type of environment, and move that to maybe Azure, where all of our production data and production models are running. Change this over to a production database, so as real data is coming in, it's producing real outputs. And we may look at this is what prod may look like for the technical team, where all of the code is blessed and everything is, from a security perspective, locked down so that it can receive this production data. And we may just put these out into a dashboard and not actually push it into the downstream application. And finally, for the business, this would this one change is what would make that model truly production. So the outputs would no longer go to this Tableau or Grafana, but rather it would go to this downstream application that it's feeding. So that's really what it looks like from lab all the way through to production, how these abstractions enable those changes to happen quickly and enable the teams to work together. And once those things happen quickly, then you can make more and more iterations and deploy more models meaningful to the business.
Excellent. Thank you very much, Regan and Garrett, for that. It looks like we have about 5 minutes remaining here, so we can do a few questions. If we do not get to your question, we will be sure to follow up after via email. First question, what are some examples of SLAs required to review in deploying or continuously running a model?
Yeah,
take that one,
I'll take that one. So, you know, one example of that may look something like this. So the data scientist has a model that is making predictions. You may see something like a confusion matrix where it has you know, false positives or false negatives that the model is producing. And you may sit down and do an exercise with your business team and say, you know, what happened? What kind of impact do each of these outputs have on the business specifically? Can we put dollars to this, or can we put risks to this? Because this is what the model is going to do while it's running in production, or what it's predicted to do. If the production data truly fits the exact same statistical properties as the training data. So, you know, we may assign some costs to those wrongful outputs of the model. You know, in a marketing example, actually, let's say that it, you know, sends marketing materials to the wrong person or somebody that actually doesn't want to buy the product. The cost associated with that is just the cost of the model or of the marketing piece that you sent out. So if it's a low cost, it's like 20 cents, then your loss is at 20 cents. Nobody bought a product from that. So maybe it's okay for your model to be 70% accurate or 60% accurate, because you still profit if you hit enough right people who actually purchase the product. So if the product's like a $200 value, you can sit down with your business and do these types of exercises and ensure that we understand the performance and the financial impact the model is having on the business.
Right, and I'll just follow it up with a slightly different concept, which is there's also SLAs on this process. So the business teams we talk with are now asking the question of how quickly can I move this thing into production and then iterate? So in addition to the actual like performance of the model itself is, you know, I want to set up a process by which I can onboard new business value in a deterministic way. So I should be able to take a model from dev to production with a deterministic set of steps and processes that take me 3 weeks or whatever the right number is. So there's also an SLA just on the practice of bringing machine learning and other models into the business.
Next question coming in. Can you explain again, high level, how technology supports the MDLC?
Yeah, sure. I'll just take that one very briefly. I think we touched on it a little bit, but I think it's important that the technology stack that's applied for, you know, the post-creation environment is quite flexible and as agnostic as much as it can be to the choices being made upstream and downstream. So, you know, supporting the variety of tools and languages that the data science team is using seems like an obvious one, but also then thinking about the infrastructure choices, like how do I create abstractions for the IT and data engineering teams so that their lives become easier? And how do I make sure that the business teams can ride on top of this abstraction to get value for the business? So again, I think the technology choices being made here, you know, we have one approach to this, again, you know, fast score, but I think it's all about supporting the variety of things that are being thrown into this kind of overall data science stack. It's just a very rich and complex area.
It looks like we have a couple more questions in, but we are short on time, so we'll be sure to follow up with everybody that has asked a question after. Again, thank you everyone for joining. And if you have any questions for Garrett or Regan or Open Data Group in general, please feel free to email learn@opendatagroup.com and we'll get back to you as soon as we can. What I'll say to everyone listening in is that we are very happy to also meet with you individually and your teams, either over the phone or in person, and go through some of these concepts and any questions you might have in more detail. And I just want to say one more time, thank you again, Reagan and Garrett. I hope we see all of you again on the next webinar.